Okay, before I get going, so I'm wondering, any lessons people learned from milestone 2? Is there any life lesson you learned from it? Any lesson you learned from milestone 2? No? Okay, it's very definitive. Is there anything you did in milestone 2 that you're not going to do for milestone 3? So I'm going to go to C07. What did you learn? Okay, start early. I would say that's a lesson that much of the class every year learns, including this year. I looked at the submission timestamps. There are an awful lot that are like 2 minutes to midnight, which is probably kind of stressful. So for milestone 3, good advice, start earlier, especially when you're doing something you haven't done before. You don't want to leave it to the last minute because you don't quite know how long it'll take. If you've done it 100 times before, you can actually be pretty confident, okay, I can get it done. But if you haven't done it before, it's more risky. Any other lessons people learned from milestone 2? Thoughts of things that you'll apply going forward? Okay, C07, go for it. Sorry, let me turn it up. I think I got you turned off. Go ahead, say it again. Yeah, graphical design can take a long time because there's no endpoint. So that's another reason for agile design, right? Get something going, because on almost all projects of reasonable complexity, you run out of time. So you get the most important stuff going first, because you think, what happens if time it runs out right now? Okay, so good points. B07, let's go to you. Where is B07? Right there.
For us, is that also want to use to see if we didn't get much of the structure just going up. And you see, and with like the way the data source all of the things the muscles will take long.
Okay, so you're saying in milestone 1, you created data structure storages, but maybe not as well organized as you'd like. And then in milestone 1, you created data structures, but they weren't as well organized as you'd like. And in milestone 2, you found that got in your way. Yeah, so it's another actually important lesson of, as software ages, and this isn't a really long software project, but you're still going to find there's some time for your software to age. It's important to have some time to go back and restructure things. And if you're in a rush, you leave it to the last minute, you've got no time for that. So it gets hard. It's actually called, there's a name for it. It's called technical debt. When you're in a rush and you're just coding, you don't have time to go back and fix things up. You're accumulating technical debt. It happens all the time on all projects. But the reason it has a name is it's important to then set aside some time to go back and fix it up. Now, in this course, the course ends, so you could say, I'm never going to pay off some of this technical debt. Fine. But in projects that keep going for a long time, it's important to go back and fix it up. Okay, so yeah, don't leave it too late. Get something simple going and improve it, and leave some time for going back and improving your software. Those are all good advice. Okay, so what we're going to talk about today is some more algorithms that'll be useful for milestone 3. So we talked about the user interface part. We started talking about the algorithm part, but we're still not up to kind of the best shortest path algorithms. So what we were talking about at the end of last week, was that we needed to store a bit more data to make sure that as our path search algorithm was proceeding, we kind of didn't overwrite important information. We didn't find one path to a node, and we stored the reaching edge of how did I get here, and then later on we got to that node again using a different path that wasn't actually as good, and we overwrote the reaching edge and we kind of messed up the results of our algorithm. When we did our backtrace, we were going to find the wrong path, the one that wasn't as good. So we need to store a bit more information. So far in our wave element, this is our to-do list. We've got the node that we should look at next. We've got the edge that we use to reach it. In order to avoid kind of messing things up, having a later path overwrite the data from a better early path, we want to store, there are a few ways to do this, but the kind of most straightforward way and most robust way, what I'd recommend is you just store the travel time. Okay, so that is the travel time. What's the best travel time, or what is the travel time to this node? Okay, it's in my to-do list. What would be the travel time that I've reached it with? Okay, I'm going to make a handy constructor. So once again, a struct is just a class where all the members are public by default. This class or struct, I'm not really trying to abstract anything, I'm just trying to group some data. And to keep my code short, I've made a handy constructor, okay? So that's all this is here. Okay, so that's one of the things I need. I'm gonna store a little bit more information in my wavefront. What is the travel time? And then I'm gonna store also a little bit more information in my node data structure. So remember, my wavefront is kind of my to-do list. After I take things off the wavefront, you know what, that's kind of gone. I need a longer term memory as well. So for every single node, every single intersection ID, I store some information about how have I gotten here in the past. So we already have been storing this reaching edge. You know, what was the street segment I used to reach you? I'm also going to store the best time that I've ever seen to get to this node. Okay? So how am I going to use these? Well, basically, I update that breadth first search algorithm that I showed last class a little bit. It's mostly the same as we had before. You know, while we still have things in our wavefront and we haven't found the destination, we keep looking. And the way we look is we say, let's take something out of the wavefront from our to-do list, get that node ID. And now before I do anything, you know, before I was just saying, okay, look at what it can reach. Look at all the edges going out of it, all the street segments going out of it. Let's look at all those nodes, put them in the wavefront. Now I don't do that unconditionally. Before I put something in the wavefront, I check, is the travel time that I just found, okay? So this thing that I just took off my to-do list, it's got a certain travel time to this node. Is that travel time better than the best time I ever found before to this very same node? If it isn't better, it's a longer path to the node, then I just want to skip everything. Okay, so I won't do anything. I'm just going to go back, keep going through the while loop. Does that make sense? So I just don't want to explore anything that's not, both it's a waste of time, and it's even worse than a waste of time. I could actually mess up some of my data. So I just do this check. That's the only change to the algorithm. Okay? The rest of this is basically what I've showed you before. There's one other thing I have to do. So let's say I have found a better path to this node. Okay, so I pass this if statement. Okay, well, when I put things on the wavefront, you notice I'm putting a little more data in my wavefront. I'm putting in what is the node that I'm going to, what is the edge that I used to reach it, and I'm also putting in what is the total time to reach that new node, which is just the time to this node, where I am right now, plus any additional travel time to get to that next node, which is just going to be you computed this in milestone 1. What is the travel time for this street segment? That out edge is a street segment. Plus, you have to pay attention, is there a turn? If there's a turn, you've got to add that travel time in as well. So that's the only other change. We're basically putting the time into the wavefront as well. And all the rest of this code you've seen before. Is everybody with me? Does it make sense? Okay, sounds good. Okay, so how fast is this? There are basically a couple different ways. I've essentially shown you a couple different ways to code breadth first search. So the first one is, well, all breadth first search uses a wavefront. Okay, so it has this while loop that says, while the wavefront isn't empty and you haven't found the destination, keep going. And now there are two basic ways that you can code breadth first search. I haven't shown this, but you could use a visited flag, just like we did for depth first search. So you could say, first time I hit a node, I'm going to mark it as visited. If I hit it again, I'm not going to look at it. If you do that, then you're only ever going to process each node once, just like for depth first search. And if you go back and you look at this loop, you know, the work that you do in this loop, once I'm inside processing one node, it's order 1. Okay, I just look at all the edges going out of it, which in a street map is, you know, about 4 edges, so it's order 1. So if I take order 1 work times no more than n intersections that I'm ever going to do work on, that's about, for Toronto, about 100,000 intersections, and I actually know what the constant is. Okay, so you wouldn't know this, but the constant is around 10 to the negative 7th. I can do an instruction in about a nanosecond, maybe a little less than that. It takes me around 100 instructions to process a node. So when I multiply this out, it's going to be pretty fast, less than 1 second. Okay, so breadth first search is fast if you use this visited flag. But it has a problem. If I just use a visited flag, the way that we've coded it so far, it won't guarantee that I get the best path. You know, the first time I reach a node, I'm going to say it's visited. If there are better paths to it later, won't look at them. So it will be really fast. It'll take less than a second, but it's not going to get the right path. What we just looked at is basically doing re-expansion. We can't guarantee that we only look at a node once. In fact, generally we'll look at a node many times, because every time we get to a node, we take it off the wavefront, we check, is this travel time better than the best travel time I had before? If it is, we say, let's do some more work for this node. Let's go and figure out the travel times to all of its neighbors. Let's put them all back in the wavefront. So, and that basically, I showed you a minute ago. That's when we use this if statement. Before deciding to process a node, we check if the travel time to it is better than the best time we ever found before to that node. It's harder to bound this one because we could visit a node many times now. So it can be a lot slower. And let me show you how much slower. So let's see, let's discard that. Okay, so this is depth first search. So, which we studied a couple, maybe 2-3 lectures ago. So let's just remember what depth first search did. Remember, it was recursive and it kind of wandered all over the place. So we didn't really like depth first search, but it's order n. I've slowed it down for animation, but depth first search is fairly fast because it only visits every node once. Okay, now I'm going to click on this. I'm going to change to breadth first search. And this is breadth first search where I am allowing nodes to be visited multiple times. So let's click on that. It looks more orderly. You can see it's kind of going out in this wavefront. You can actually see the wavefront. That didn't take too long, and it got a good path. 11.3 minutes travel time, so that looks pretty reasonable. Let's go a little further. Okay, so it's going a little further. It's expanding out. And you notice that it kind of slows down. The reason it's slowing down is it keeps finding new paths to nodes that are shorter, and so you can't see it, but it's kind of redoing work over and over again. It keeps redrawing these blue lines because it's looking at them multiple times. So it's kind of wasteful. And you see once in a while it finds something new to do, but it's basically redoing work a lot. It still hasn't found the destination. Hopefully it will soon. I think it's getting there. What's that?
Where's the destination?
What?
Where is the destination button?
Oh, it's just where I clicked. So it's basically going from here to there, okay? So from green to red. It found a good path again. It took 11.3 minutes, but that algorithm was getting kind of slow. And it was the re-expansion that was doing it. So let's see if we can do better. And spoiler, you can do better with like only a small amount more code. Okay, so how could we limit this re-expansion? Let me show you let me show you this again at kind of a higher level. Okay, so what breadth first search, the way we've coded it right now, is doing is it starts expanding out. It's expanding this wavefront out around the source. Okay, so it's going along, and maybe it's found a whole bunch of relatively long street segments, and so it's made a fair amount of progress towards the destination. So it's almost there. But then it's also been following a bunch of like relatively short street segments. And it turns out that that was actually pretty fast. It found a little route down residential streets that's like super annoying to the residents, but it found it. And that means it's found faster paths to all these nodes, which means it's now going to want to like look at, okay, let's look at all their neighbors, put them back in the wavefront. So it's going to redo tons of work. It's going to expand out from those new paths. And eventually it finds the destination. But basically all this overlapping was kind of a waste of time. You kept looking at the same nodes over and over again as you found different, better paths to them. Okay, so let's look at what our code looks like. So this is my breadth first search algorithm. I'm using a linked list as my wavefront. And the reason I'm using well, let me ask this in a second. Basically, while the wavefront isn't empty, what I keep doing over and over again is I say, take the first thing out of the wavefront. Okay, check. if that node that I just took off, this is a new better travel time. And if it is, I record that. And then I basically take all of its neighbors, all the things it can reach, and I basically push them into the back of the wavefront. So my wavefront is basically a FIFO queue. The first thing that goes in is the first thing that comes out. So it's a nice orderly checkout line at your grocery store. Nobody's cutting in line. It's all good. Okay, so I put things in here, and then eventually I take them. So I put them in at the end with this push, and I take them out at the front with this pop. Okay? Because actually, let me ask you a quick question. Let's just see if people are thinking about data structures. Why did I use a list for this? As I've told you that vector is a really nice data structure. When in doubt, I usually use vector. I didn't use vector here. Why did I use a list instead of a vector? Because I do like vectors, okay? So if there's no reason to use something else, I'm just going to use a vector. It's nice and easy to think about. Okay, so C07. Yeah, why did I use a vector? And let me turn on your mic.
Because you say one of the first milestone, or after you need to copy the whole vector, and for this, you can just delete that one. So basically, it's the deletion time as 1.
Yeah, that's exactly right. Okay, so basically, the way I'm using the way I've built this wavefront, where it's a FIFO queue, I'm basically taking things out of the front, and in a list that's order 1. You just remove it from the front, you delete it, it's all fine. The head pointer gets updated inside the list, but it's all fast. And a list also has a fast pushback. This is also order 1. So fast with a list. If I had used a vector, pushback is fast, this is order 1, but removing things from the front of a vector is slow. It's order N. You have to take the thing out of the front, shift everybody over by 1, it's kind of a mess. Okay, so I don't want to do that, which is why I use the list. So it's nice that STL gives me this menu of data structure choices because I just picked the right one. Okay, so that's why I've done it this way. How can I make this code more efficient? So I can't make it more efficient just by recoding it. I have to rethink the algorithm a little bit. So right now I'm using a FIFO queue. So I find new intersections that I can reach, and I put them at the back of this queue. And then I basically take a new intersection of my to-do list from the front. Okay, so everybody goes in order, they come out in order. Does it seem like you could do better? Any ideas of how you might do better? So I'm going to clear this. Yeah, so I'm going to go to, all right, I'm going to C07. C07 is like running the table here. So you guys have to jump in sometime and like see, your team can answer it too. Okay, so go ahead.
See that the algorithm is sort of looking at intersections all over the place. Maybe we can define a box. The line was between the destination and your origin. And so if you are looking at intersection very far from the box, you will just look at it.
Yeah, so that's the right idea. Okay, so you're saying, why are we just saying, let's put whatever intersection we reach first, we put it in the queue, and that's the one we're going to take out next. Why don't we have some intelligence, right? That's, which ones seem more promising? And that's the right idea. So the next couple of sets of algorithm enhancements we're going to make are both in that direction. How do we make smarter choices about what to take out of this wavefront? Okay, so I'm going to go to B09. So you had some ideas about, like, maybe you can look at where you're close to the destination, hold those ideas. Okay, so we're going to do those in a little while, but there's an even simpler one to start with. So B09, let's see, where are you? Yeah, what do you think?
Oh, I'm thinking of something, I'm recalling something called priority queue, and does it have anything to do with this?
Yes. Okay, so you're saying you're not exactly sure what to do with it, but you think something called a priority queue might be helpful. Is that right? And you're right. Okay, so you've got a good memory for something that might be useful to you. Okay, so any other thoughts? So priority queue, in case that gives anybody any ideas, like that name sounds interesting. This is just a regular queue, a first in, first out queue. Priority queue is a little different. Okay, all right, so the basic thing we want to do is we want to change how we put things in this wavefront and how we take things out so that we minimize node re-expansion. Okay, we don't want to keep finding new paths that are better to some node that we've already done a whole bunch of work expanding outward from. And a really good idea is instead of just taking whatever node is next in the wavefront, we should take the one with the smallest travel time. Okay, so we see we've got some travel times of 5 seconds, 12 seconds, and 20, and the 20 is in the front. What if we don't take that 20? What if we actually go through this list and we say, well, there's something with a smaller travel time. Let's look at that first. Okay, so let's say we just try that. In algorithms and data structures next year, you'll prove that this is a good idea, so I'm not going to prove it, but I'm just going to show why it works, or show an example of how it works. This is pretty intuitive that this makes sense. Okay, so this is the graph where we had a problem before. And we started our source. Okay, so our algorithm always starts with the source. We put in our wavefront, node 0 and 0 seconds. Okay, I'm not showing the reaching edges because I don't care about that right now, but that would still be in the code. Okay, so that's not my destination. So I'm going to look at all of the outgoing edges. And I'm going to find I can get to node 1 and I can get to node 2. So I'm going to put both those in the wavefront. Okay, and I'm going to put them in with the time, the total time it would take to reach them, which for 1 would be 20 seconds, and for 2 would be 5 seconds. Okay, now I'm done processing node 0. I take the next thing out of my wavefront, but I don't take this one, right, which is what I used to do with breadth first search. I would just take the first thing. I'm actually going to look through the whole wavefront, and I'm going to take this one because it's got the smallest time. So I'm now going to look at this node 2. Okay, so I take that out of my wavefront, and I'm going to say, okay, it's not my destination, but it can reach node 1, and it can reach it with a total travel time of 5 plus 5 or 10 seconds. Okay, so I put that into my wavefront, so it's here. Now I need to go to the next step. I look through the whole wavefront again, I find that's my smallest travel time. So I'm actually going to go look at node 1. Okay, and node 1 isn't my destination, but it can reach node 3 with a travel time of 16 seconds. So I put that in there. I go through the wavefront. This is still the smallest entry. Take it out. Not my destination, but it can reach node 4. So I put node 4 in with a total travel time of 19 seconds. Now I pull it out because it's the smallest entry. It's my destination. I invoke my backtrace algorithm now. So my backtrace algorithm just follows back these edges, which I didn't show them in the wavefront, but we were recording them as we went along, just like the algorithm I showed last week. So when I backtrace, I'm going to find follow edge E, D, C, right? I said follow C there, and B, and I'm going to get that path. Okay, which is actually the minimum path. So this finds the minimum path much more efficiently because it's following the most promising paths. Does that make sense? Okay, so if you want to, you can go find proofs online of why this gives the perfect answer. It actually is not guaranteed to give the perfect answer with the turn penalty that we've given you, but we'll still get good answers. Okay, so if anyone realized that, you go, wait a sec, with turn penalty, is it guaranteed to get the best answer? No, not unless you actually augment this algorithm, which you do not have to do for milestone 3. Okay, it'll still get quite good answers. Did you have a question or are you just thinking about it? Okay, let me turn on your microphone. So, yeah, go ahead. Say it really loud. So I'm having trouble hearing. Okay, so you're saying, you know, what if, just tell me if I got this right. You're saying, what if this time, let's say this wasn't 3 seconds, let's say this was 5. Is that right? So if that was 5 seconds, then this wouldn't have been 19, this would have been 21 seconds, right? So I would have still gone back, I would have gone through the wavefront, I would have found node 1 has the smallest travel time. so that's right. I would take it out, right? And I would say, okay, node 1 with 21 seconds of travel time. I will look at it, but I've still got that if statement that I put in before. Let's see, let me show you the if statement. I still have this if statement in there, okay? So I will pull it off, but I'll say the travel time that I just pulled out of the wavefront for node 1 is 20 seconds, and I've already got it best. I've already recorded that there's some way to get here in only 10 seconds. So I won't do anything. I'll look at it, I'll say you failed the test, I don't do anything else, I go on to the next thing. Does that make sense? Yeah, so that less than is still useful to me. Okay, so yeah, this finds the shortest path with, if we didn't have a turn penalty, this can actually be coded so that it does no re-expansion. With the turn penalty that we put in, it's a little more tricky. You will typically get a little bit of re-expansion, which is why we still want that if statement that I showed you. Check if the travel time is less for this node before you do anything else. And this algorithm is important enough that it's named after this person who discovered it, Dijkstra. Okay, so this is a building block of lots of algorithms, right? This is a really good shortest path algorithm. It's basically a pretty small enhancement on breadth first search. So breadth first search is really the core of this algorithm. And Dijkstra's algorithm just says, sort the wavefront. Take the smallest travel time, and it's going to be more efficient. Okay, does that make sense? So you want to remember that name? Okay, this is the first good shortest path algorithm we've come up with. Dijkstra's algorithm works pretty well. If you code it for milestone 3, you'll pass the vast majority of the tests. You might not pass the absolute hardest CPU time tests, but you'll be close. Okay, so it's a pretty good algorithm. And we're going to talk about some enhancements, but those enhancements are very small amounts of code. So Dijkstra's algorithm is kind of the basis for them anyway. Okay, but before I get too excited about talking about how fast this algorithm is, we got to think about how we're going to code it. So right now I've got a linked list wavefront. Okay, that's the way I've coded it. How much work is it? Say this is my wavefront. How much work is it for me to get the smallest entry in my wavefront? Okay, I'm just going to clear people. So what do you think? If I've got some number m, let's just give this a new number. So we'll call that m. What is the work? And I'm going to go to B09. What's the work to get the smallest entry? With a linked list, okay?
I suppose only the smallest entry, I think it should be m.
Yeah, that's exactly right. Okay, so it's order m, okay? Which isn't very good. So insertion is fast. I'm putting things at the end of the list. I'm still doing that. But with a linked list, I'm going to search through when I want to get the smallest element. I'm going to look through every single one element in it. So if there are m elements in it, it's order n, pretty slow. I mean, it depends how big m is. So in theory, I could have every single node in my whole graph on the wavefront, in which case this order m becomes order n, which is really bad. In practice, that's a bit unlikely. Usually my wavefront is kind of like the perimeter of a circle. Now everything inside I've explored, and on the wavefront is kind of the edge. So in that case, it's still pretty big. It's the square root of it. So either way you slice it, it's not very fast. Okay. What can I do that's better? Okay, and I'm going to go to you because you said it earlier. What can I do that is better than a linked list? Linked list is not, it was a good choice when I was doing a FIFO queue, where I was taking something from the front and I was putting something in the back. Everything was order one. It is a bad choice once I want a priority queue, which is what I want now. A priority queue means I want to get the smallest element out of this. So it's very capitalistic, okay? There's no longer a fair queue where people go in the back at the shopping mall. People are cutting all over the place according to who appears to be the most promising. So yeah, this is your chance. What do you think? Priority queue?
I'm not really sure what priority queue does.
Okay, so you want a priority queue, but you're not quite sure what it is. Fair enough. Anybody have an idea of how to implement a priority queue? What could we use that is faster than this? Yeah, so let's go to B06. And let me make sure I get, okay, go ahead.
Is it possible that the more we insert like critical power or all of the
Sorry, I had some trouble hearing that because we're starting to get feedback. So you can do this with data structures you already know. Okay, so you're looking for something where you can put stuff in quickly, because we're going to do that a lot. And where you can put stuff, okay, sorry, I'm playing with all the microphones. You're looking for something where you can put stuff in quickly, because we're going to do that a lot, and take it out quickly. But when you take it out, you want to get the smallest element, not just the first element or something like that. So is there any data structure that you know that is pretty good for that? So, okay, go ahead.
I'm thinking of generations maybe, or
It's a good idea. Okay, so binary search tree. So what is the complexity to insert something in a binary search tree? So go ahead. You're still active. What's the complexity to put it in a binary search tree?
inserting could be live and removing is also live.
That's right. Yeah, that's exactly right. So it's a much better trade-off. A binary search tree we can insert in log, and we can actually find the smallest element, just the leftmost child in a binary search tree, also in log time. So a binary search tree is way better, okay? So if we did a binary search tree, insertion is log m and remove smallest is also log m. So if you remember back to 244, you probably learned, if you want to ever get the minimum in a binary search tree, just keep going down all the left children, right? That's the technique. It's still logarithmic. Just have to check one entry per level. Okay, so how much faster is that? So a linked list, we're basically going to look at n nodes. We're going to look at we can look at every single intersection in the city map, and every single time we want to figure out which node to look at next, we can do between n to the 0.5 and n if we use the linked list. So for a binary search tree, we're going to be order log m, where m is how much is in the wavefront, and that's for sure less than n, right? So it's going to be less than or equal to log n. Okay, so if we basically multiply this out, we say we might look at every single intersection once. If we don't have a turn penalty, we can actually guarantee we'll only look at each intersection once. With a turn penalty, we might occasionally look at them more than once, but it's still pretty close. Basically, this multiplies out to a linked list is between n to the 1.5 and order n squared. And using my, about 100 instructions to process a node kind of rule of thumb, this is a big range, anywhere from 3.2 seconds to 1,000 seconds. So it could vary a lot, but it's relatively slow. With a binary search tree, if I put these numbers in, I'm going to get well under a second. So it makes a really big difference. You need to use the right data structure. So a binary search tree is a good choice for this. This is kind of a hard question. You might not be able to answer this, so I'm going to answer in a minute. Is there anything better than a binary search tree for this application? So a binary search tree completely sorts its data. And we actually only care about finding the minimum. We don't really need the data fully sorted. So have you ever heard of a data structure that is even better than a binary search tree for such a thing? There is one, and I'll give you a spoiler. I don't know who's buzzed in at this point. Is E07, are you buzzed in on this question or a previous one? Yeah, I'm going to put you on. Sounds like you might have an idea. Okay, so go for it. Have you heard of any data structure that would be good for this, even better than binary search tree? A heap, yeah. So there's a data structure called a heap, which is even better. Okay, binary search tree will work pretty well. Both log n, insert, and delete is pretty good. But yeah, there's another important data structure. It's not quite as important as a binary search tree, but you'll probably hear it mentioned in your career many times, called a heap. It's got the same asymptotic complexity or big O notation. So insertion is order log n and removal is order log n. So they're actually the same as a binary search tree, but they're faster by a constant factor. It's probably 3 or 4 times faster. Why is it faster? The reason it's faster is it doesn't fully sort its data. A binary search tree is doing more than you need because you don't need everything sorted. You just want to find the minimum quickly. So a heap, binary search tree, remember the left child is always less than the right child, which means that if you look at the whole tree, it's completely sorted. So a heap has a weaker sorting criteria. It's basically that the key of the parent is always less than the key of its children. So this node has a key of 3, and its children have keys of 20 and 36, so it's smaller. And then if I look at it, that's true at every level. So if I look at this node, its key is 20, and that's less than the keys of its 2 children. And that is satisfied everywhere in the heap. Okay? What this means is that the smallest entry is at the root of the tree. We can get it really quickly. Which is great for a priority queue. Okay, but there is no ordering between nodes at the same level. So in a binary search tree, this is the left child, it would be less than 35, because that's the right child. In the heap, it's not true. Okay, so I can't make any assumptions about the ordering within one level, I just know between levels. Okay, so let's look at one of the operations you're going to do with a heap. One of the operations is pop. Take out the smallest element. Okay, and I'm just going to walk through it to show you that it's not that complicated and it's fast. Okay, so I want to get the smallest element, and I know that's actually at the root of the tree, so it's really easy to get. Just look at the root of the tree, there's your smallest element. And I want to take it out of the heap because that's what I'm doing in Dijkstra's algorithm. I'm taking out the smallest element, I'll process it, I don't want it in the heap anymore, so it's got to be gone. Okay, so it's gone. This isn't a heap anymore, right? It's got a hole at the top, so I need to fix it. So the way you fix it is you actually take an element from the last level, okay, so a large element, and you put it in the top, which is the wrong spot, and then you do a bunch of local comparisons to get it in the right spot. So you compare it with its 2 children, so it's going to compare with, it's going to compare with these 2. Okay, and it's going to swap with whichever one of those 2 is the smallest. So 20 is the smallest, so it's going to swap. Okay, now it has to do that. We have to do that comparison again. I have to check against the 2 children underneath it now. Okay, the smallest one is 35, so it's going to swap with that. So after we've done this, we're actually back to a heap. The smallest element is back at the top, and for every node in the tree, it's always smaller than both of its children. Okay, so the amount of work that we just did is logarithmic because we only did one compare and swap operation at every level. The number of levels is logarithmic in the number of things in the heap. So this is log n. And it's actually less work than we would do in a binary search tree by a constant factor. So it's a bit faster. I'm not going to show this, but the approach to put something in the heap is very similar. Okay, you basically put it at the bottom. So I put something new in, maybe 15. I would actually put it at the bottom, and then I would compare to my parent, move up if I should, and then compare every level until I get to the top of the heap. So it's basically almost the same operation, just starts at the bottom. So that's also log n. Okay, so does everybody grasp the basics of how a heap works? Okay, so I'm going to go to C07. So you have a question, let me unmute you.
Question for the binary search tree, you have order of log certain height, but for the list you have order one certain height. Do you think that it will count when calculating the height capacity?
Yeah, so your question is, these are not order 1, these are order log n. When we set the time constraints, do we take that into consideration? Is that the question?
Right.
Yeah. The time constraints are reasonable, so don't worry. We don't make them up arbitrarily. The way we actually set time constraints for this, like milestone 3, it's complicated. We can't just analyze how fast should your program be. So we wrote a reference solution. We actually wrote various algorithms inside of it, from simpler to best that we could think of. And then we make different CPU time tests. So the very hard is you're comparing against our best algorithm, which we're going to teach you. It's coming next. And we never expect you to be as fast as the reference solution. So we always multiply by, for all of the tests except very hard, we multiply by 2.5 times. So you can be 2.5 times slower than our reference solution with the equivalent algorithm. For the very hard, it's our best algorithm, which is coming next. It's A star. And you can be 1.5 times slower than that. Okay? Does that make sense? So it means you can be a little sloppy in your coding. And the truth is, when we wrote our reference solution, we didn't micro-optimize it either. Like myself and the TAs are actually in a hurry too. So we have the exact same kind of agile development constraints as you guys have. We didn't sit there like banging away on it forever.
Okay, I see that. Just for the binary search tree, it's giving faster.
You can, I mean, you can actually code this with a binary search tree and you would probably be able to pass our speed tests, okay? But you've made life a bit harder for yourself. If you, instead of using a binary search tree, use a heap, your code is going to be faster by, a small factor, and it's not any harder to write. But if you're just like, I love binary search trees, I'm going to write it that way, yeah, you can probably pass all the speed tests that way as well. You're just making life a little harder.
Okay.
Does that make sense? Okay, so actually on that question, who's going to go code a heap after this lecture? How many people will go code a heap? Okay, so E07 is going to code a heap. Anybody else going to go code a heap? Okay, what are other people going to do? It's going to go work on 231? Like, you could do that. So we probably eventually want to code something. What are you going to do? Yeah, it's on the slide. Okay, this is in STL. So I'm explaining how a heap works because it's important. As engineers, this is a big part of your skill set, is to actually understand what's going on under the hood. But it doesn't mean that you should actually go code this. It's not actually that hard to code, but it's a lot easier to just ask STL to do it. In STL, this is called a priority queue. Okay, so the implementation of a priority queue is a heap. Fastest known data structure for this problem. The STL container is called a priority queue. It's actually a very simple container. It has pop and it has push. Pop takes out the smallest thing. Push puts in the biggest thing. I mean, heaps can be done for either the smallest thing is popped out when you ask for, give me something, or the biggest. Okay, so you have to pay attention to that. You do not want the biggest travel time, you want the smallest. But you can do that in STL. Get a priority queue to give you the smallest element, it'll be efficient. Okay, so let me quickly demo this. All right, so we just did breadth first search, which got really slow. But let me show you breadth first search maybe one more time so you remember it. Okay, so breadth first search, and it gets really slow if you get far away. Okay, so it starts off, it's not too bad, but then it slows down. Actually, this is getting kind of painfully slow. Okay, so I got bored. I'm going to stop it. Okay, it's still going, hasn't found the destination yet. Okay, so let's change this to, let me go through the algorithms here. Okay, let's change this to Dijkstra's algorithm. Okay, so it's a lot faster. I'm slowing this down with the animation. Actually, the virtual machine is slower than BNC, so I'll probably slow it down less next time. But Dijkstra's algorithm kind of makes steady progress because it's not doing all this re-expansion. So it's almost reached it. There, it found it. Okay. And let's do another one over here. Okay, so it's much better than the breadth first search that's kind of re-expanding over and over again. And Dijkstra's is a good algorithm. So code this up, it'll work well. And my laptop is significantly slower than the UG machine, so I'll basically have to readjust my animation speed. Okay, so Okay, do you think, you just watched that, do you think we can do, yeah, so go ahead, C07. Yeah,
Yeah, they can just saw the, you put that last point, it didn't take the volume for the map, but it traversed the entire map.
yeah, that's actually, it does work. I mean, it's possible that by me clicking on various buttons and getting bored that I did something weird. So, but I've never seen it not find the path. And Dijkstra's algorithm is guaranteed to do it. As we're animating there, when I click on a button to change it, we're kind of like killing the algorithm in the middle. So it is possible I managed to do something weird there by getting bored. Okay, did you have a question as well, or? Okay. Okay, can we do better than Dijkstra's algorithm? Okay, so let me show you Dijkstra's. It's kind of at a higher level again. So Dijkstra essentially expands, you kind of saw this in that demo, it kind of expands out in all directions. It's like going out in circles. And it's pretty efficient because it gets rid of all this re-expansion and so on. And it backtracks, we find our path. But you can see that, you know, the odds that the shortest path from here to here actually go the wrong direction for a long period of time. You know, so you're trying to go north, but for a long time you're going south. That seems pretty unlikely. So it does seem like we're wasting quite a bit of effort actually searching in the wrong direction. Okay? So any ideas? How could we do better than this? You buzzed in? Okay, let me go to you. Go ahead.
I'm still in your class, but I think there's something called SPFA or something. I'm not entirely sure, but it's all something based off of CFS and
Okay. Well, so you're right. It is still going to build on what we've done. So we're not throwing away our algorithms. We're just going to augment them a bit. So that's the right approach. We're going to augment it. I'm going to go to E07. So yeah. Okay. So only go closer to destination. Makes sense. I mean, this is what a human would do. If you asked me to find my way to Young and Steeles, I'm probably not going to start walking off towards the waterfront. So go towards the destination. Makes sense? Let's see. Okay, so C07, what do you think?
So back to the origin and the destination, and it's looking the intersection outside the box. I think the box a bit larger as well. So then looking to the out of the box, the skipper.
Okay, so I didn't catch all of that. So maybe just give me a quick summary. Can you, so it's harder, say it really loud. Try one more time.
So you can draw a box, draw a rectangle from the origin to the destination.
Okay.
Yeah, and while we are moving the intersections, if the intersection is far from the box, we don't have to skip that intersection.
Okay. Yeah, it makes sense. So you're saying basically prune intersections outside the box, outside of a bounding box. Makes sense? Any other ideas? Okay, so I'm going to go to, back to E07. Yeah, go ahead.
Let's say, one scenario, if you put this little tiny bit outside of the rectangle, you're able to get on like a highway or something.
Yeah.
And it doesn't.
Yeah. That's exactly right. So both of these approaches are reasonable. Okay, only go closer to the destination or don't search outside the bounding box, but they both risk suboptimality. Okay, what do I mean by that? It's exactly the case you just said. What if there was a freeway right here? I'm right by the 401. I'm going a long way, but I just never go to the 401 because it's outside my bounding box. I take local roads all the way. Could actually be a lot slower. So these are the right ideas. Essentially, you're coming up with pruning functions. You say, do not explore options that don't satisfy this criteria. You have to, that's a good idea. We're going to do things kind of like that, but you have to be careful. If your pruning function is too strong, you won't find the shortest path, or you will risk that you don't find the shortest path in some cases. And we are checking in milestone 3 that you find, either the shortest path or very close to it. So you'd actually risk failing those tests. So, so let me just quickly highlight, this is kind of the approaches that have been suggested so far. Let's say that we only look at nodes that are closer they're closer to our destination than where we are right now. So I'm at some node, I'm looking at this new node. If it's closer to the destination, I'll look at it, otherwise I won't. Mostly seems like a good idea, but let's say the highway 401's in between the two nodes, and I can't just run across the highway, right? So I have to go around some local roads. I have to go through this underpass. I have to take some local roads, and I have to get back to it. So this red arrow and this red arrow both went in the wrong direction. They both took me further from my destination. And if I didn't allow that, I would never find the solution. They would also fail the test of what if I drew a bounding box? If I drew a bounding box around this, I would only look for something straight across. If it didn't exist, I'd actually say no path exists. So these pruning functions are a little bit too harsh. So what we're going to do next class is we're going to look at something that's a little less harsh, okay? We're not going to prune, we're not going to throw away solutions, but we're going to sort them. We're going to change how we put things in the wavefronts and how we take things out of the wavefront so that we look at the most promising solutions first, but we're going to do it in a way where we guarantee that we're still going to find the best answer, okay? And we'll talk about that on Wednesday. Okay, thanks everybody.